Jumping right in, let's begin by understanding what IP or Internet Protocol is. Picture this. You're sending a postcard to your friend across the country. You write the message, put the postcard in the envelope, and then you jot down your friend's address. The postal service then takes your postcard and delivers it to the exact location you've written down. That's exactly what IP does. But instead of postcards, we're talking about data packets. Now you might be wondering, what is a data packet? Well, think of a data packet as a tiny bundle of information. This could be anything from a part of an email you're sending, a photo you're uploading, or a video you're streaming. These data packets are like the lifeblood of the internet, constantly circulating and delivering information. But here's the thing, the internet is a vast and complex network. So how does a data packet know where to go? Well, that's where the Internet Protocol comes in. IP is a set of rules governing how data is sent and received over the internet. It's like the postal service of the digital world, ensuring that these data packets reach their correct destination. And just like your friend's home has a unique address, every device connected to the internet has a unique identifier known as an IP address. This IP address is a critical part of how data finds its way across the internet. When you send an email, stream a video, or visit a website, your device's IP address is used to ensure the data you're sending or receiving ends up in the right place. So, in simple terms, an IP address is like your home address but for your device on the internet. It's a vital part of how the internet functions, ensuring that data can be accurately sent and received across this vast network. And with that, we've unraveled the mystery of the Internet Protocol. Now let's dive deeper into the world of networking. Having understood IP, we now move on to TCP or Transmission Control Protocol. TCP is like the rule book for the internet. It's a set of protocols that outline how devices should establish a connection and exchange data over a network. This World Wide Web of computers and servers, all communicating with each other, relies on these protocols to ensure that data is sent and received correctly. Now, let's imagine the internet as a vast ocean and data as ships sailing across this ocean. TCP, in this scenario, would be the harbor master, guiding the ships, ensuring they dock safely and in the right order. It's all about control and order, making sure that data gets to where it needs to be without getting lost or scrambled along the way. But how does TCP achieve this? Well, it works hand in hand with IP, our earlier topic. While IP is responsible for addressing and routing data, TCP takes care of the delivery. It's like a tag team duo ensuring your data reaches its destination safely and correctly. TCP checks for errors during transmission. If a ship, or in our case, a data packet goes missing, TCP will notice and send out a search party. It also makes sure that the data packets arrive in the correct order. If they're out of sequence, TCP rearranges them, ensuring the message makes sense at the destination. So you see, TCP plays a crucial role in maintaining the integrity and reliability of the data we send across the internet. It's the behind-the-scenes hero, making sure our emails, web pages, and file transfers arrive intact and in the right order every time. In summary, TCP is all about delivering your data reliably. It's like your trusty postman, braving the elements to ensure your letters, or in this case data packets, reach their destination safely, completely, and in the right order. It's a complex system, but absolutely essential for our daily digital lives. So TCP is like your reliable postman, making sure your data gets to its destination in one piece and in the right order. Now that we have a grip on IP and TCP, let's explore the two versions of IP, IPv4 and IPv6. To start, let's look at IPv4. Introduced in the early 1980s, IPv4 is the fourth version of the Internet Protocol. Its primary role is to identify devices on a network through an addressing system. The issue with IPv4 is that it uses a 32-bit addressing scheme, which allows for just over 4 billion addresses. Now, considering there are more than 7 billion people in the world, each with multiple devices connected to the internet, you can see how we might run into a problem. Enter IPv6, the solution to this limitation. IPv6 was introduced to replace IPv4 and overcome the shortage of addresses. It uses a 128-bit addressing scheme, providing a nearly infinite number of addresses. To give you an idea, that's enough addresses for every grain of sand on Earth. But it's not just about the numbers. The structure of IPv4 and IPv6 addresses is also different. IPv4 addresses are written in decimal form, separated by periods, while IPv6 addresses are written in hexadecimal form and separated by colons. For instance, an example of an IPv4 address might be 192.168.1.1, whereas an IPv6 address could look like 2001, 0db8, 85A3, 0000, 0000, Ada2E0370, 7334. Moreover, IPv6 also introduces other enhancements in comparison to IPv4. It includes a simplified packet header for routing efficiency and improved support for extensions and options. In short, IPv6 is the upgraded version of IPv4, providing a virtually unlimited number of addresses. It's like moving from a small town where everyone knows each other by name to a bustling city where everyone has a unique identifier. So, as we continue to connect more devices to the internet, the transition to IPv6 becomes inevitable. With IP and TCP clear, it's time to understand UDP or User Datagram Protocol. UDP is a protocol, much like TCP, that is used for sending and receiving data over an IP network. However, there's a fundamental difference between these two. While TCP is diligent and thorough, ensuring that every bit of data is received in the correct order and checking for any errors, UDP is a bit more laid back. Now, don't get me wrong, it's not that UDP doesn't care about your data, it's just that it's got a different set of priorities. UDP is all about speed. It sends data out into the network without waiting around to make sure it's received. And it doesn't bother checking if the data is received in the right order. It's like that friend who's always in a rush, leaving a trail of chaos in their wake, but somehow manages to get things done. This fire and forget method makes UDP faster than TCP, but it also makes it less reliable. If a packet of data gets lost somewhere in the network, UDP won't know, and it won't care. There's no system in place to resend lost packets. You might be wondering, why would anyone use UDP if it's less reliable? Well, there are certain applications where speed is more crucial than accuracy. Think of live streaming videos or online games. You're more interested in getting the data quickly rather than ensuring every single bit is accurate. A minor glitch in a video or a tiny lag in a game is preferable to waiting for the buffer wheel to spin, right? So, while TCP is like a meticulous mailman who ensures every letter is delivered correctly, UDP is like a speedy courier who doesn't bother about the order of delivery or if a parcel gets lost. It's all about getting things done quickly. To put it simply, UDP is like a speedy courier who prioritizes speed over ensuring every parcel is delivered correctly. Finally, let's look at how data is sent using TCP and UDP. Imagine you're sending a precious package. You wouldn't just toss it into the mail and hope for the best, would you? No, you'd want confirmation that it arrives safely and in one piece. This is precisely how TCP, or Transmission Control Protocol, operates. TCP first establishes a firm connection between the sender and the receiver. Think of it like a handshake, a mutual agreement that the data exchange is about to take place. Once this connection is set up, TCP begins transmitting data. But TCP doesn't just blindly send packets. Oh no, it keeps tabs on each one, ensuring that all data is received and in the correct order. If a packet goes astray or arrives in a jumbled mess, TCP is right there to retransmit or rearrange. It's like a careful packer, meticulously ensuring everything is in its rightful place. Now, let's switch gears to UDP, or User Datagram Protocol. Unlike TCP, UDP doesn't bother with handshakes or confirmations. It just starts sending data, no questions asked. This might sound reckless, but there's method to the madness. By skipping the formalities, UDP can transmit data faster than TCP. However, it's a bit of a gamble. Packets might get lost or arrive out of order, and UDP won't lift a finger to fix it. It's the speedy courier, prioritizing pace over precision. So, in the grand face-off between TCP and UDP, who wins? Well, it's not that simple. Each has its strengths and weaknesses, and the best choice depends on what you value more, reliability or speed. Do you need every bit of data to arrive safely and in order, or are you okay with a few lost packets in the name of speed? So when it comes to sending data, TCP is like a careful packer ensuring everything is in place, while UDP is all about speed.